going to start with Z-tree. Z-tree is a collection of symbolic reasoning engines, right? You can also view it as automatic term prover. Z-tree is joint work with Nikolai Bjorner and Christoph Wintersteiger, who have many engines there, but basically Z-tree uses heuristics to select these engines. The user has some flexibility in selecting them, but they are mostly black boxes. Okay, I said that Z-tree is automatic term prover, but the technical term for a tool like Z-tree is a satisfiability modulo theory solver. I'm going to give an example of what a SMT solver can do. If you send this formula to Z-tree, it will come back saying it is satisfiable. What it means is that I can find values for x and y that would make this formula true. We call the solution a model. And we can also send another problem to Z-tree. It's a small variation of the first one, but this one, Z-tree would say is unsatisfiable, and it would return a proof, right? Some people would say this is a certificate because the proof is not fully detailed, but some people managed to reconstruct this proof in other systems like Isabel. How Z-tree is used? Basically, for instance, a test case generator, a bug finder like Sage, would convert execution trace in your program into a formula and send it to Z-tree. A verifying compiler like VCC would check if assertions in your code can be violated or not. In both cases, you're creating a formula and asking Z-tree if this formula is satisfiable or not, if there is an assignment that would make this formula true. If such assignment exists, for example, in the case of Sage, we are exposing values for the input values of your program that allow you to exercise a particular path, execution path in your program. These symbolic reasoning engines like Z-tree have many applications in industry and academia. You have test case generation tools, verifying compiler, invariant generation tools, model-based testing, model checking, like the CBMC is a kind of model checker. Some people use for type checking. At Microsoft, there are many tools that use Z-tree. I'm just listing a few of them. Z-tree had both impacts on industry and academia. It's used by many research groups. It's also used in many popular systems like Isabel, PAX, Sage, SLAM. There's a device driver verifier, Visual Studio. And for example, just to give an idea on how successful a tool like Sage is at Microsoft, Sage, for instance, creates more than 5 billion constraints, 5 billion formulas, and sent them to Z-tree when it was checking Windows 8 and Office. And Sage runs 24/7 looking for bugs. I like this quote from Zohar Mana. The logic is the calculus of computer science. Right? So you have this complexity ladder. Z-tree can solve problems in many different places in this ladder. My point here is that you have high computational complexity, right? And in practice, it's infeasible to expect that we can solve problems anywhere in this ladder, right? Even SAT can be extremely hard, right? But we can try to solve problems we find in practice, right? In real applications, in software verification applications, in test case generation tools. For instance, test case generation, I think bug finding, test case generation are one of the most successful applications of Z-tree, at least in the industry. Security is critical. The main point of Sage is trying to find the $1 million bug, right? Here's some numbers. The cost of Microsoft security bulletins is on the order of millions of dollars. The cost of adultery worms sometimes goes to billions, right? And many of these attacks they use basically try to modify files that your application parses, right? Or packets that your application is going to decode. For instance, internet browsers parse dozens of file formats, right? And hackers try. They use random testing. They try to mutate files until they find a vulnerability. And now, They also use tools like Sage. Don't be fooled. I mean, they are using the same kind of technology to find vulnerabilities, right? Sometimes we get emails from Russian hackers asking questions about Z3. No, this is true. There was one guy that contributed code. He uses a mask. You can only see his eye on GitHub. Sage. Sage is based on this idea of directed automated random testing. The idea is the following. You start with your program, you start doing random tests, random execution, getting random inputs, and you try to exercise many execution paths in your program, creating random inputs. Eventually, you're going to find out that some paths you cannot exercise because you have to use non-trivial combinations of your input file to exercise the path. For these paths that cannot be executed, Sage is going to create a set of constraints, a big formula you can view. Sometimes this formula has several megabytes. It's going to send to Z3, and Z3 is going to produce the input, if it terminates, the input that allows you to exercise this path. Okay, we talk about these bug finding tools. Let's talk now a little bit about software verification. Right, in software verification, you have tools at Microsoft like F-Star, VCC, Boogie. There are many others. I just select 3 because I like the logos. All these tools, you have specifications. You're going to annotate your programs with contracts, invariants, field and type annotations, and so on. Most of them use a program logic like Dijkstra, weakest preconditions. And they have a verification condition generator, right? There is a module in these systems that is going to convert these annotations in formulas that have to be verified by Z3. So far, so good. For easy problems, these tools are great, right? Because everything is automatic. But when your application, what you are trying to verify, the complexity starts growing, you start having stability issues and proof stability. What do I mean by proof stability? Is when you make a small modification in your program and the proof breaks. Sometimes something completely irrelevant as renaming a variable, right? And this issue happened in many cases, right? You have the Hyper-V that was a verification effort to verify the hypervisor that runs between the hardware and the operating system. You have the Ironclad and Iron Fleet projects, the Everest that's trying to have a certified implementation of the HTTPS protocol. You can learn more about these projects in these links. But then you may ask, well, why the test case generation tools are so successful and these ones have these issues, right? Well, the problem is that's where they are in the ladder, right? The software verification tools are here. The bug finding tools are here, right? That's the problem. Another thing problematic is tools like F-Star. The mismatch between the logic accepted by F-Star, by Z3, and F-Star is huge. F-Star is also based on dependence type theory. Later I'm going to tell you that Lean is based on dependence type theory. This way, you have F-Star that's based on dependence type theory, and you're trying to create formulas in first order logic. That's what Z3 can consume, right? This way, you have, in the case of F-Star, 2 problems. The distance between the logical foundations of F-Star and Z3 is huge, and you have the problem that you are dealing with problems that are undecidable. Okay, to deal with these problems, we start moving to the direction of Lean. Lean is trying to work with Jeremy Avigad, Mario Carneiro, Forrest Van Doorn, Gabriel Ebner, Johannes Rose, Rob Lewis, Judge Rush, Daniel Selson, and Sebastian Ulrich. Many of them are here. And the main goal of the Lean project is bridge the gap between interactive and automated Z3 improvers, right? Z3 is what we call automated tree improver, but you have many interactive tree improvers that are very successful, like Coq, Isabel, Hall Light, and so on, ACL2, right? And let's talk a little bit of Lean. Lean is relatively new. It's not that so new, but we started in 2013. It's an open source to improver. And now some of us view it also as a programming language, but it starts only as a tier improver. It's a platform for software verification, formalizing mathematics, and developing domain-specific languages. Lean is based on a small trusted kernel. If you care about trust, Lean is a good target. It's based on dependency type theory, right? Then the mismatch between F star and Lean is much smaller than the mismatch between F star and Z3. And the main idea, at least the one we started in Lean, is that we can have partial constructions. Suppose that you are having a stability problem, you can give a skeleton of your proof and use the automation only on the holes that can be reliably discharged by Z2, a tool like Z3. Right? That was the first, the basic assumption we had when we started developing Lean. But Lean it now has features like modern programming languages, like you have inductive data types. We even have inductive families like tools like Agda and Coq. We have recursive equations to make it convenient, but this is just surface syntax. Behind the scenes, is all being compiled in primitives that are accepted by the kernel. Proofs in Lean, you can use a mix of trying to write like a textbook proof. Here we are using like a calculational style proof, giving step by step. You decide how much detail you want to provide. Here are the proofs for each step. This is not a realistic example, it's just to show what you can do. You can write the proof yourself. You can ask automation to create the proof for you. Lean here is showing that it's polymorphic. You can parameterize it by structures like rings. This is a term that is going to work for any ring structure, any instance of a ring. Just to give an idea on how the proof language looks like. Well, but in Lean 3 that we started in the middle of 2016, we had another, I think, we moved Lean in a slightly different direction. We introduced metaprogramming. The idea is that allow users to extend Lean using Lean itself, right? And give access to users to the internals, right? Now the user can write Lean programs that use the type inference procedures that are inside Lean, use the unifier, use the simplifier, combine these things, and use the decision procedures. For instance, decision procedures that before were in black boxes like in Z3, now are available for users to use, right? And they don't have to learn two different languages. You can write your specification using Lean, and you can write your automation using Lean too. Here is a very small static that you can write in Lean itself, and actually that's how this static is written in the library, right? The first line, we have this meta keyword. What does that mean? In Lean, a meta definition is a definition that is supposed to be used only for metaprogramming. We are not going to check, Lean is not going to check that if meta definitions terminate or not. It doesn't care, because it assumes that you don't care about proving properties about your meta programs. You care about proving properties of your programs, your definitions, your regular definitions. In this way, your program doesn't need to terminate. A meta definition can use a regular definition. For instance, we are using the list. Lists is inductive data type. We have a list library, and these are all regular definitions. In this way, from meta, you can access regular definitions, but not the other way around. In this program, what is going to do? You have an expression that you can view as a formula, and a list of expressions. If the list is empty, we are going to fail. If the list has at least one element that we're going to call age, we are going to infer the type of age, and we are going to try to unify with E. If it unifies, we return age. Otherwise, we keep searching. This is the or-else operator. You try to do that. If it fails, you continue searching, right? Then there is assumption static. What this static does, he gets your local context, all the variables that are in your context, or you can view also as all hypotheses that are in your context. You get the type that you're trying to synthesize. Then you say, try to find, in my context, something, a variable, a hypothesis that has the type of what I want to synthesize. And if this fails, return the error message, assumption static failed. If I ran this static here, my local context has 4 elements, P, Q, H1, and H2. And you want to find a variable, a hypothesis here that has the type that matches the target, that unifies with the target. In this case, it's going to be H2, right? This static may look simple, but most interactive TM improvers provide this static. We reflect the expressions, right? The linear expressions, the data type that represents linear expressions is described here. No surprises. You have for bound variables, you have free variables, meta variables, sorts, constants, applications, lambdas, pies, and let expressions. This is, I don't have time to explain this. This is the universe, Lin's universe polymorphic, like systems like Agda and Coq. And here's just a small program that's given expressions is going to count the number of, suppose that you have f of a is going to return 1, f of ab is going to return 2, f of abc is going to return 3. Right? It's just a basic recursion. Now I will just flash a few statics that have been implemented in Lean itself. For instance, one is this position prover that Gabriel Ebner implemented. It's 2,200 lines of code. So position prover is the kind of prover you find in tools like E, Spaz, Vampire. Many hammers use these tools. And here I'm just showing the state of the prover and showing that after you specify the state of the prover in Lean, you can extend the static that represents your statics with this extra state. Here's another example. I have here a glist. This is very common in Haskell, this data structure. The mainglists are like lists, but they have an O1 append operation, right? Suppose that you define your glist library. You probably have a regular list library too, right? And these two structures are isomorphic, right? Then to automate the process of moving lemmas from one structure to another, Johannes implemented a tactic called transfer. To use transfer, you have to first relate operations onglists with operations on lists. For instance, you're going to say that the append, if you append to the lists and convert to a list, you get the same results of converting the first lists into a list and appending the result of converting the second list into a list. You prove these lemmas and you prove for other operations, and now you can transfer automatically. We know that the list append is associative. We have this proof. Now you can just use this static to reliably transfer these results to the lists, right? This will not fail. It's very robust, and that's the main point. The structures, you don't need to have, you can also transfer results from net to int. It has many bells and whistles, and it's using the Lean library. Now we come full circle. From Lean, you can also call Z3 now. The idea is that we was actually Jared that wrote a tactic for converting a Lean goal into a Lean problem into a Z3 problem using Lean itself. The Lean API, he can translate Lean formulas into Z3 formulas using Lean. He can create a process, a Z3, running Z3 using Lean. He can create a file with a Z3 problem using Lean. And it's basically a translation process. You start with a Lean goal, a lemma, something here is something trivial that you can say now by Z3. He's going to convert these intermediate formats that he calls low-order logic. He wants to call LOL. And he keeps applying transformations until you can call Z3. Of course, this static is not going to support everything that's available in Lean, but if you have a goal that has only arithmetic, Boolean connectives, right? Uninterpreted functions, you can use this pipeline. I don't have time for the last example. I will do the conclusion. I will go to the conclusion because I want to make a small demo of Lean. Okay, what are the main takeaways from this talk, at least in my point of view? The first thing is that SMT solvers like Z3 are very successful in bug finding tools, right? The CBMC is a successful tool, and from our point of view, is a bug finding tool. Sage is very successful, is a bug finding tool, right? But for software verification, at least when you're trying to verify non-trivial programs, we always run, at least in the experiences we had, we always run into scalability and profitability issues, right? We are trying to address these problems with Lean by having a system that's trying to bridge the gap between automated and interactive to improving. The first idea that I'm trying to convey is that if a proof is unstable, you can, as a user, provide a skeleton of the proof that Lean can check. And the holes that can be reliably discharged, you can call a tool like Z3 or something equivalent that we're going to have in Lean. The second takeaway that users now can create their own automation. They can extend and customize the system using Lean itself. They don't have to learn another language. They work in a completely integrated environment. One thing that you can attack is that something that was really hard in Z3 to do is sometimes you have domain-specific applications that you can create algorithms that are very specialized for them. But Z3 is a general purpose solver. It doesn't make sense to implement solutions for every possible domain you're going to face. Right? But with a tool like Lean, you can build domain-specific automation. Right? The internal data structures and procedures are exposed to users. It's not a black box anymore. Right? Now we call that white box automation. I have a few minutes. Yeah, I'm going to make a small demo. For instance, this is Visual Studio Code running Lean. We have tools like type inference. If you hover over definitions, you're going to get their types. You have tools like, for instance, let me show a proof. Here is a proof using tactics that were written in Lean. For instance, if you want to see the implementation of cases, you can say, pick definition. You're going to find its definition there. You can see the implementation of your tactics, right? There are very few primitives that are implemented natively. Most of our tactics are implemented in Lean itself. You can, if you want, you can jump to the definition, to the file that defines it. We have tools like auto-completion. We also have the red squiggles like modern environments that's going to tell you there's an error here, saying what's the error. If you want to use auto-complete, it's going to give you, let's make it more interesting. Okay, now there are 4 options. You can select which one do you want. It's really nice when you're proving a lemma using tactics. You want to see the effects of tactics interactively, right? One thing you can do in Lean, you can inspect. It's going to show you the tactic states, and it's completely, you can see everything, step-by-step execution of what is going on. I mean, after you apply cases, it shows you the results. You can simplify, then you can see the result of the simplification, and you can see step-by-step what is going on. Sometimes, even a tactic like rewrite that is you want to be very precise about the rewriting rules you are applying. You can see after each rewrite, you can see what happens in your goal. Users can also, if they want, they can see the fully elaborated term, the term that was sent to the kernel. Let's see another thing. You can, as a user, also let's see if I find one that, for instance, you can annotate your tactics with doc strings. Let me jump to change. You can document your own tactics, even the ones that you implement, and this is going to be available automatically in your environment. That's the point. We are trying to combine tools like SMT solvers, the technology behind SMT solvers with the technology available in interactive improvers. Users can extend Lean using Lean itself. They can implement their own automation. And our point now is that with this kind of technology, we can create, our hope that we will be able to create much more reliable proofs. Thank you very much.